Okay, so quick sound check. This should be working now. Let's see. Yeah, so this should be working. So I'm gonna begin. So this is the second session for algebra, where we're talking about properties of algebraic operations. We talked about addition and multiplication last time. Um, we and Today I want to start off by talking about the distributive property and the so-called factoring, which is essentially the distributive property backwards. So let's try and discover the distributive property here together. I'm gonna start working in this window here. This is my draw pad. And let me just make sure. Yep, it works. Okay. There we go. All right, so we have Jake, and Jake has 5 cats and 7 dogs. Okay, so 5 cats, 7 dogs. For each cat and each dog have 4 legs. So 4 legs each. Now, first question is, how many legs total do the cats have? Okay, so you say, how many cats do I have? I have 5 cats. Each one of them has 4 legs. That's 5 times 4. And so you say there are 20 legs that cats have. Second question, how many legs total do the dogs have? So it's a similar question. You have 7 dogs. Each one has 4 legs. And so 7 times 4, and you have 28 legs. This is for cats. This is for dogs. Third question, how many animals are there? Well, we had 5 cats, 7 dogs, and so in total we have 5 plus 7, which is 12 animals. Lastly, how many legs total do all the animals have? Well, I have 12 animals. I have 20. Well, in total, how many legs do I have, right? I have 20 legs coming from cats, 28 legs coming from dogs, and I can just add them. And I can get 20 plus 28, which is 48 legs. Right? Now, another way you could have done this is you could have said, how many animals do I have? I have 5 plus 7 animals, right? 5 cats, 7 dogs. How many legs does each animal have? 4. So 4 legs per animal for each one of these 5 plus 7 animals. And this is, of course, 48, right? 5 plus 7 is 12, and 12 times 4 is 48. But you could have counted the same thing by saying, I have 5 cats. That's 4 legs per cat, plus 7 dogs, and that's 4 legs per dog. And you will get the same thing, which is 48. So this right here, this expression right here, is what we call a distributive property, right? We've distributed the multiplication into this addition. So we see that, again, we're counting the same thing here. If I want to know the total number of legs, what do I say? I say, in the first example here, let me see how many animals I have in total. I know that each animal has 4 legs, so I do 4 times the total number of animals. In the second example, I divide my animals into 2 groups. Okay, that's the key to distributive property. You divide this into groups. First group are my cats, and for each cat, of course, I have 4 legs. And then second group is the dog group, and for each of those, I have 4 legs. And I add the total number of legs in each group, and I get the same 48, right? So essentially, you're doing this. Imagine you have animals here. Each dot is an animal. Each animal has 4 legs, right? Each one of these dots has 4 legs. And now if I asked you how many legs are in here, you could have said, okay, I'm going to count. That's 1 dot, 2 dots, 3, 4, 5, 6, 7. There are 7 dots, 4 legs each, 7 times 4, 28. That's this way of doing things. You counted the total number of dots and multiplied by 4. Or you could have said, maybe these 3 dots right here, these 3 dots on the right, they're bold, okay? They're bold dots. So you say, okay, let me split this into 2 groups. I'll have the bold dots and the non-bold dots. How many legs for the bold dots? Well, if there are 3 of them, each one has 4 legs, right? That's 3 times 4, 12. How many legs for these guys? Well, there are 4 of them. Each one gets 4 legs, and that's 16. And if you add those again, you get 28, right? So distributive property in this sense is just dividing your space into groups and counting whatever it is you're counting in each group and then summing up your results. All right, let's go to the next example here. Let me just quickly check something. Yeah, we're there. Okay, next example. There are 9 children in the Connor family. So we have 9 children. Their parents buy 99 goldfish and 72 angelfish. So you have 99 goldfish and 72 angelfish. If each child receives the same total number of fish, then how many fish will each receive? So what we know is that each child gets the same number of fish. Gets the same number of fish. And the question is, what is this number? Okay, well, you could have said this. You could have said, how many fish do I have in total here? Well, I have 171 fish, right? 99 plus 72, I believe, is 171. So this is the total number of fish. Now, relating this to the previous example, what I'm doing is here's my space of all the fish, right? I am counting all of these dots. My dots here are fish. I'm counting all of them, saying how many dots do I have in this space, and I have 171 of them. Now, I got to divide all these 171 into 9 groups, right? Into 9 for 9 children. How do I do that? Well, 171 divided by 9. Okay, you can do this division, and this is how many fish each child will get. So what is another way we could have done this? We could have said, okay, if each child is to get 100, if each child is to get the same amount of fish, right? How can we distribute this fish so they all get the same amount, of course? And now you can divide it into groups. Instead of saying let me count all the fish simultaneously, you can say let me first count the goldfish. Suppose right here, let's draw a boundary for the goldfish. Here are the goldfish. These are 99 here, and these are the angelfish, and there are 72 of those. Now, we're going to say each child is to get the same amount of goldfish and the same amount of angelfish, right? So if there are 99 goldfish, how many will each child get if there are 9 children? Well, 11, right? Because 11 times 9 is 99. So each child gets 11 goldfish. And then how many angelfish will each child get? Well, you take 72 and divide by 9, and of course you get 8. So 8 angelfish. So in total, how many fish does each child get? They get 19. Okay, and if this is correct, if this computation is correct, it should be the same here. 19 should be the answer to this division. Let's check. If I do 19 times 9, do I get 171 again? Well, 10 times 9 is 90. 9 times 9 is 81. And I add these two, and I do get 171. They match. Okay, so again, this is distributive property at work, sort of visually, right? Because in the first scenario, we said, how many fish do I have in total? I have 171. Now divide that into 9. or divide 9 into that, whatever, divide that by 9 to distribute the fish equally amongst all the children. The second way we did it is we said, let's group our fish into all the goldfish and all the angelfish. Now I want to distribute the fish equally among all the children. So I have 99 goldfish. How many should each child get? Well, 99 divided by 9 is 11. And you do the same for angelfish, right? 72 divided by 9 is 11. And we see that in both ways of computing this, the answer is 19 fish. Each child should be getting 19 fish. Now, how do we write algebra? These are all examples, but how do I write the distributive property in its most general form, right? As an algebraic formula with symbols. And the way I do that is this. I say some number multiplied by the addition of two other numbers allows me to distribute the multiplication. So I multiply by the first number in the parenthesis plus multiply by the second number in the parenthesis. Okay? And this works both ways. So I can move the multiplication over here. Why? Because we talked about the fact last time that multiplication is commutative. So this is the same as b plus c times a. So a I can move to the right because of the commutative property. Okay. So there we go. That's the distributive property in its most general, written in its most general form. Okay, so what is factoring then? Well, factoring is going the opposite way, going from here, from the right side of this equation to the left side of the equation. Because this is an equality, right? It says whatever's on the left side equals whatever's on the right side. So that works the other way as well. Whatever's on the right side should be equal to whatever's on the left side. Let's see how this works. If I tell you 4 times 3 plus 2, okay, here's an example, and I tell you use the distributive property. You say, okay, I know that I can distribute whatever is here into these parentheses, into the addition. So I get 4 times 3 plus 4 times 2. And now going back, this is sort of the forwards. Let's write it this way. This is forwards direction. Now what is the backwards direction? Now we start from here, from the right side. I give you 4 times 3 plus 4 times 2, and now I say factor it. So this backwards direction is what algebra books often call factoring. Realize this is just the distributive property. So you're working in the opposite way. You say, okay, I see this equality. What can I do? I can take out the a, write my multiplication sign, and then everything else goes in the parentheses with a plus. Let's do that. I take out my a, which for me here is the 4, times, and then in parentheses, what am I left with from this group? I'm left with the 3, right? There's that b, the 3. Plus, what am I left with from this group after I take out the 4? Well, I'm left with the 2. There it is. And that's factoring. Okay, keep working backwards from the distributive property. Why is this useful? So when we start doing algebra, or we actually are already doing algebra, but when we start doing a lot of computations, things like this, 99 plus 72 over 9. Now you can say, okay, 99 plus 72 is of course 171, and then I can divide by 9, etc. But you can also notice that both 99 and 72 are multiples of 9. They're both multiples of 9. So if I could somehow take out that 9 and cancel with this bottom one, I'd have no division. I'd just have addition here. So can I bring it? So let me rewrite that. Let me rewrite both 99 and 72 as a product of 9 with some number. So 99 is, of course, 9 times 11 plus 72 is, of course, 9 times 8. We have over 9. And now we look at this expression in the numerator and we say, oh yeah, that is factoring. That is, we can use distributive property in the backwards direction. What do we have to do for that? We have to take out the common part in both groups. What is common to both groups? The 9 is. Let's take it out. We take it out times, now we open parentheses. What are we left with in the first group? Well, we're left with an 11. What are we left with in the second group? An 8. There we go. Over 9. And now the 9's cancel, right? Because we're multiplying by 9, then dividing by 9. So if you multiply by 9, divide by 9, nothing happens, right? So you can cancel those. And you're left with 11 plus 8, which is 19. So be on the lookout for common multiples. Okay, then factor them out and cancel. This is common. This is all over high school mathematics in general. Calculus uses this heavily when you get into limits, so it's good practice to start paying attention to this stuff now. Okay. Let's see. And one thing I want to remind you of is this. If you have a fraction that looks like this, 3 plus 9 over 2 plus 9, remember that you cannot cancel the 9's. Okay? Canceling only works when the numerator and the denominator are products. You have to have products, not addition. Notice I canceled here. I had a product here. Here it is. This is product. Whatever's in parentheses doesn't matter. That's one expression. It's a single number, right? If you look at it, 11 plus 8, that's one number, 19. But I'm multiplying two things here, whereas here I'm adding two things. So canceling will only work when you're adding. Remember that. Okay, let's move on. Now let's do some exercises before I actually start covering equations here. We need to get good at some of this stuff. All right, so the first exercise says the following. We want to evaluate each of the following, first by computing the expression inside the parentheses, then by using the distributive property. So if you remember last time we said, when we were talking about the order of operations, we said whatever is in parentheses, we do first. And that is still true. But we now have another option. So we could, if I want to compute the following, 2 times 8 minus 3, we can use our order of operations and we can say 8 minus 3 is, of course, 5, and 2 times 5 gives us 10. Second way we can do it is we can say, okay, now I know how to use distributive property, right? And if you're confused by the negative sign, remember that minus 3 can also be rewritten as an addition. So this can be written as 8 plus negative 3. Okay, minus 3 is the same as plus negative 3. I strongly suggest you do this every time if you're confused by minus signs, and this will save you a lot of trouble. Just rewrite it immediately as plus the negative number. And now we can use distributive property, right? 2 times 8 plus 2 times negative 3. So 2 times 8 plus 2 times negative 3. Now 2 times 8 is 16, plus 2 times negative 3 is negative 6. And what is 16 plus negative 6? 10. Same as here. So we now have two options. We either rely on our knowledge of the order of operations and do what's in parentheses first, or we apply the distributive property. All right. Now I'm not gonna do too many of these because I actually plan on uploading a picture of all these exercises so you guys can practice. So I'll do one more. 8 minus 13 times negative 3. Now this is the same situation, right? You can say, all right, I can do the order of operations and 8 minus do the what's in parentheses first, then do the multiplication. Now, first things first, I see a minus sign, 8 minus 13. Say it throws me off. I know what to do. I write it immediately as an addition. There we go. Times negative 3. Okay. So now, let's first do this with the order of operations. 8 plus negative 13 is negative 5, right? Negative 5. So we have negative 5 times negative 3. Now, we saw last time that negative times negative is, of course, positive, and 5 times 3 is 15. And I'm done. Or you can apply the distributive property, right? It's negative 13 times 8, negative 13 times 8 negative 3, excuse me, not 13, negative 3 times 8 plus negative 3 times negative 13. Negative 3 times negative 13. Negative 3 times negative 8, that's negative 24. Negative times negative becomes positive, so if plus positive 3 times 13 is 39, right? So what is 39? So negative 24 plus 39. Now, if this confuses you, right? You see a negative 24 plus 39. You're not quick yet. Remember that you have here, what we have is addition of two numbers. Here's the first number. Here's the second number. What do we know about addition? It's commutative. Swap them. Swap the places. 39 plus negative 24. Why is this better? Because now the larger number is on the left. It's easier to work with. Okay, so 15, you're done. Same as above. So order of operations or distributive property, both will work for these kinds of questions. Oh, so, okay, I just read the comment in the Discord channel. There will be Google Hangouts for sure. But I just realized that Google Hangouts, for some reason, when I'm connecting to, when people join the Hangouts, a lot of the times the voice problems, the problems with the mic, they actually intensify. And so I need to look into what's causing this. There's something within the Google Hangouts connection. I need to look through the settings. So we'll get there. I'll fix that, and there definitely will be Hangouts. For today, just the YouTube channel though. All right, next. Okay, this one's kind of nice. So we have Richard, and Richard writes this: negative 2 times 5 minus 3. Okay, then Richard says this is the same as negative 2 times 5. So Richard is doing the distributive property, right? Negative 2 times 5 plus negative 2 times 3, right? Negative 2 times 3 times 3. Okay, now Richard says, I know negative 2 times 5 is negative 10. And I know that negative 2 times 3 is negative 6. And so Richard says my answer is negative 16. Now the book tells us that Richard is incorrect. This is not the correct answer, and the question is, where did he go wrong? The place where he went wrong is the thing that I warned you to always do as a preliminary step, at least for now. Look what he wrote. He wrote a plus sign here, right? When we have a minus. Now, where's the issue? To see where the problem is, let's rewrite the minus sign as an addition of a negative number. So we'll rewrite this as negative 2 times 5 plus negative 3. I haven't changed anything. It's the same expression. Now I apply my distributive property. So negative 2 times 5 plus, now I see that plus sign, negative 2 times, and here it is. Here was the problem, times negative 3, not positive 3. Okay, so this is, in essence, this is not a 3. It's a minus 3. You can't just disregard that negative sign. Minus 3. Okay, so we get negative 2 times 5, which is negative 10. Now, negative times negative is positive, so we get positive 6. And the answer is, of course, negative 4, not negative 16. And this is a very common mistake. I've seen this error a lot, okay? So I strongly recommend it. If you're taking algebra at school for the first time and you're going through this stuff, as soon as you see a minus sign, I really recommend you rewrite it this way. It'll save you a lot of headache. Eventually, you'll get used to it, and then you'll stop doing this. But for now, I recommend you do it. Okay. Let's go to factoring. So remember what factoring was. It was distributive property in reverse. Let's look at a few examples here. So suppose we want to add this, 88 plus 16. Okay, you can do this, but the numbers aren't the smallest, right? They're not the smallest numbers. Can I simplify? And you say, okay, this is a multiple of 8, and this is a multiple of 8. Let me rewrite it that way. So what multiple of 8 is 88? 11. What multiple of 8 is 16? 2. Do I see the common part in both groups? Sure, it's the 8, right? Let me pull it out. There it is. Times. Now we have our parentheses. What is left in this first group when I take out the 8? The 11. There it is. 11. Plus, what is left in the second group after I take out the 8? The 2. And so now I have 8 times 13. Okay. Now, which one of these two computations is actually easier? I'll leave that up to you, but I definitely wanted to show you the distributive property here. Okay. And I'll do one more. 92 minus 160 plus 36. Okay. Again, I see a minus sign. First thing I'm going to do is I'm going to write it as addition of a negative number. Just not to get confused. Okay. So I look at these three and I think to myself, are these multiples of anything? Well, I know 36 is a multiple of 6. 160 is also a multiple of 6, or is it? Is it or isn't it? Okay. How about what? I mean, what can we do? How can you check? If you're not sure, how can you check? You always have your regular division, right? Let's try it. So if you take 160 and try to divide it by 6, what do you get? Well, 2 times 6 is 12, and you have 4 left. And the 0 comes down. So can 40 be divided evenly? Can the 6 divide 40 evenly? Right? No, it doesn't. So you look for another multiple. You say, is there another number that all three of these are divisible by? Well, 92, I know, is 8 times 7. I'm sorry, 8 times 9. 8 times 9. So 8 or 9. How about 9? Is 36 a multiple of 9? Well, I know that 9 times 4 is 36. So yes, it is. What about 160? Is 160 a multiple of 9? Suppose you're not sure. Okay, let's try to divide again. 160 divided by 9. Well, if I take 1 9, what will I be left with here? A 7. And if I bring a 0 down, does that work? Okay, so in this manner, you will go through the multiples, you'll find the common multiple and factor it out of all three of these expressions. Now, again, is it faster than just doing this addition? That depends on it's your personal preference, but in school, you will be asked to do this. I mean, you'll be graded on this. Your grade will depend on you factoring out the number. So I will post this question I will post this question on the Discord channel, so definitely go through it. And if you're stuck, if you can't finish it, let me know and I'll help you with it. Let us see what else is here. Okay, so that's about it. Maybe let me show you one more multiplication example, and we'll go to the equations. So multiplication, we can have something like this, right? 3 times 8 over 27. So now I don't have additions, I have multiplications. There's the multiplication. What do we know about multiplication? If we have a ratio where the operation that I'm doing is a product, if I had one of these numbers in the denominator, I'd be able to cancel, right? So you ask yourself, can I rewrite the denominator somehow as a product of one of these that has one of these numbers in there? And you say, yes, 27 is 9 times 3. There it is. And I can cancel the 3's. Okay, this is a product, so we know we can cancel it. If it were addition, we can't. Product, we can. We're left with 8 over 9. Okay. And the last example, 99 plus 88 minus 77 plus 66 over 11. All right. Now you look at this example and you notice that all the numbers, the units digit, this digit on the right and the digit on the left are the same, right? So, and I have 11 in the denominator, and you tell yourself, I wish I wish I had an 11 multiplying this whole thing somewhere. I wish I had an 11 somewhere in the numerator so I could cancel with this 11. And now you notice that each one of these numbers is a multiple of 11, right? 99 is 9 times 11. 88 is 8 times 11. Negative 77 is negative 7 times 11. 66 is 6 times 11 over 11. Now notice each one of these groups has 11 in common, right? They all have 11 in common. We can take it out. So if you factor out the 11, what are you left with in the numerator? 9 from the first group, 8 from the second group, negative 7, notice not positive, negative 7 from the third group, positive 6 from the fourth group. And now, this right here is a product, right? So I'm multiplying two numbers. There's the first number, and everything in the parentheses is my second number. This is a product. So I know I can do this cancellation. So I do the cancellation. Now, 8 minus 7 is 1. 9 plus 1 is 10, and 10 plus 6 is 16. Why did I choose to do this operation first? I'll leave you to think about that. The reason it has to do with the order of operations. That's what lets me do this first before I do 9 plus 8. Okay, we covered that last time, so I'll let you think about it. If it's unclear, again, do ask the Discord channel. All right, so I think that's enough examples, and the rest of it you guys will try yourselves. Let's go to equations. So what are equations? To understand equations, let me draw the following. So suppose you have these scales, and let's see. Here are your scales. And over here, let's say you have something that weighs, let's say 7 kilograms. Now over here, you put something that weighs 3 kilograms. Okay, you want the scales to be even. So what do? One thing you could do is you could add to this guy something that weighs 4 kilograms, right? Because 3 plus 4 is 7. And now the scales are balanced, so you can say the total mass over here, the 3 plus 4, the total mass over here, is the same as the total mass over here, the 7. These weigh the same. This amount of mass is the same as this amount of mass. Okay, could we have done this differently? Sure. Suppose your scales are like this. You have, let's say, again, same 7 kilograms here, but here initially you have 1 kilogram. And you want to balance this out. You say, okay, let me put a 6 kilogram weight over here, but you don't have a 6 kilogram. All you have are 2 3 kilogram weights. Well, okay, let me put both of them here, right? There are the 2 3 kilogram weights together. They give me 6 kilograms, and I add the 1 kilogram, I get the 7 kilogram. Again, these weights are balanced. So this is 1 plus 3 plus 3 equals 7. Okay? So notice when we put an equality sign here, what we're saying is that whatever expression is on the left side of the equality sign evaluates to the same value as whatever expression is to the right of the equality sign. They have the same value. Okay? Now that we know that they have the same value, let's think about this. Now that we know that they have the same value, what would happen if I did this? If I said, let's add 2 to both sides. Does this expression have the same value as this expression? Well, the answer is yes, because I know that whatever is boxed was the same. They had the same value, and to each of those, I added a 2. I added the same thing, right, on both sides. So they still have the same value. This is a valid equation. The equality sign is still true. So, again, what if I go back to where I started, and what do? I add a -1 to both sides. Is this equality sign still valid? Yes, it is, because these two expressions had the same value, and I added the same thing to both of them. So they still have the same value. What if I went back to where I started, and now I'm going to multiply both sides by 4? Is my equality still true? Well, yes, these have the same value, same mass on my scales, and then I multiplied both of them by 4, the same number, the same 4. So if these two initially had the same value, after I multiply both of them by 4, they still have the same value. So this equality is still true. Okay, and finally, if I write the following, 17 minus 7 equals 9 plus 1. Is this true? Well, 17 minus 7 is 10. 9 plus 1 is 10. So yes, this equality is true because the value on the left side of the value of the expression to the left of the equal sign is the same as the value of the expression to the right of the equal sign. So yes, this is true. But what about this? If I now take whatever's on the left and I divide it by 2, and I do the same operation to whatever is on the right, is this equation still valid? Well, the answer is yes, because the numerators were the same. We established that. And to both of them, I applied the same operation. I divided both of them by 2. So if you take two things that are the same and do the same operation to both of them, the result is still the same. Okay? So this is the expression that you'll hear a lot in your algebra classes, that if you apply the same, let me write that down actually. If you apply the same operation to both sides of the equation, to both sides of an equation, the resulting equation still holds. So depending on your book, they'll express it using some variant of the statement, but you see that the point. If your original equation is true and you do the same thing to both sides of the equation, then your results are still the same, right? Your equation still holds. Now, this becomes really helpful whenever we do the following. So whenever we have two, this is going to be simple arithmetic, but you'll see why this is handy. You have 15 over 20 equals 6 over 8. I have fractions here. I have an equality, right? I'm given this equality. The book tells me this equality, so I'm going to assume it's true. I'm not going to test whether it's true or not. I'm given this equality. Now, one way I can simplify this, or one thing I can do, is let me try and multiply both sides of the equation by 20. I know I can do that, right? If I have an equation, I can do the operation to both sides of the equation without modifying my equation. We just saw this. So what I'm going to do is I'm going to multiply both of these expressions by 20. So 20 times 15 over 20 equals 20 times 6 over 8. Now, why did I do this? Well, because I have a product here, and we know that means I can cancel these two. So what is the left side of the equation now? It's 15. I have 15 left. 15 equals 20 times 6 over 8. Okay? What am I going to do now? I apply it again to both sides of the equation, always to both sides. If I do something just to one side of the equation, I've changed my equation. It no longer holds. But as long as I do the same operation to both sides, it's still valid. So now to both sides, I'm going to multiply 8. So 15 times 8 equals 20 times 6 over 8 times 8. Well, why did I do this? Because look, 6 over 8 multiplication by 8. I know that 8's cancel. And what do I have now? I have 15 times 8 equals 20 times 6. Now look at this expression and look at where we started. So you'll often hear the expression cross multiplication, with the numerator of the first one times the denominator of the second one. The numerator of the second one times the denominator of the first one. Cross multiplication. In reality, there is an operation called cross multiplication. What you're doing is you're multiplying both sides of the equation by the denominators. First, we multiplied both sides by 20. That got rid of this 20 here. Then we multiplied both sides by 8, and that got rid of this 8 in the denominator here. And that is our cross multiplication again. We're just multiplying both sides of the equation by the same number. Okay. So another example that does this is the following. So let's try to do this again. So 73 over 43 equals 511 over 301. Now, I don't expect you to work out this multiplications here, but let's try to at least follow the steps. Again, I want to come up with a new equation that is valid, that is the same as this one, that does not have any fractions. How do I do that? How do I get rid of the denominators, in other words? Well, we know how to do that, right? To get rid of the denominators, we multiply both sides by each of those denominators in turn, just like we did here. Let's start with the first one by 43 here. Let's multiply both sides by 43. And remember, it has to be both sides, otherwise you're changing your equation. So 43 times 511 over 301. And 43's cancel. So I'm left with 73 equals 43 times 511 over 301. So now I have only one number in the denominator, the 301. We need to get rid of it. How do we do that? Well, we multiply both sides by 301 again. So 73 times 301 equals 43 times 511 over 301 times 301. And now the 301s cancel on the right side. And so what I have is 73 times 301 equals 43 times 511. Notice these are the same equations, the equation that I started with and the one that I ended up with. These are the same equations. They've just been rewritten. Okay, this one's rewritten in a different form. We've gotten rid of the denominators. But the meaning of these equations is still the same. Why is it the same? Because we've been applying the same operations to both sides of the equation at each step. To both sides, we multiplied 43. Then to both sides, we multiplied 301. So when you do the same operation to both sides of the equation, you're not really changing your equation. You're just modifying the way it is written. It's analogous to the fact that I can write the number 3 and I can write the number 5 minus 2. Okay, they're just written in different forms, but they're the same thing. So it's exactly the same here. All right. Let's do the following. So let me draw this. So suppose you have a mass of 1 kilogram, and then you have a mass of 5 kilograms and 2 kilograms. On the right side, you have a mass of 8 kilograms. And I tell you that this is an equation, and your job is to write this in its equation form. Okay? Now, what would the equation form be here? Well, how much is the total mass on the left? Well, you have 1 here, you have 5 here, and you have 2 here, right? How much is on the right side? You just have 1 mass, so it's 8. Are these the same? Well, 1 plus 5 is 6, 6 plus 2 is 8. Yes, they are. Here's your equation. Okay? Now, is the difference between left sides of two equations always equal to the difference between the right sides of the equations? So let's see. Here's one equation. Let's make another equation. Suppose I say this. I say 5 minus 2 equals 3. I just made up this equation, okay? Now, The question says, is it always true that if I take the left sides of both equations and look at their difference, so 1 plus 5 plus 2 minus this expression, 5 minus 2, is it the case that it will always be equal to the difference of the right sides of the equations? So 8 minus 3. Now, notice that both of these are equations. The left side of the equal sign, let's call the first equation 1 and the second equation 2. So the left side of equation 1 is exactly the same as the right side of equation 1. That's what equality means. The left side is the same as the right side. So this right side, this 8, is exactly the same as 1 plus 5 plus 2. That's the left side, right? Now this 3 in the second equation is exactly the same as the left side of the second equation, the 5 minus 2. That's what an equal sign means. These are the same expressions. So instead of writing 3, I'm going to write the expression on the left side, 5 minus 2. And now look what our question has come down to. Look at the left side here, look at the right side. They're exactly the same expressions. So are they equal? Of course. Okay. So remember, equality, the equality sign tells you that whatever expression you have to its left, doesn't matter how complicated, whatever expression you have to its left always equals to whatever expression you have to its right. Okay, and just to drive that point home, suppose I write this, I say 3 equals logarithm base 2 of 8. So if you're in Algebra 1, I'm hoping that you haven't seen this expression before. Maybe you have. But if you haven't, the reason I'm doing this is no matter how complicated whatever is here may look, if you're given an equal sign, that tells you that this whole thing, whatever may be here, is just 3. Okay, they're the same expressions. They have the same value. Okay, let's do another example. So this one says you have two equations. 15 minus 8 equals 7. Second one is written this way, right below here is 6 equals negative 5 plus 11. Now, part A says multiply the left sides and multiply the right sides. Are these two products the same? So the question asks us, if I so let's call this first equation 1, second equation 2, and the question says, if I multiply the left side of the equation 1 by the left side of equation 2, okay, left side of equation 1 by the left side of equation 2, is this going to be the same as multiplying the right side of equation 1 by the right side of equation 2? Is this going to be the same? Now again, what you might have done is you might actually go and compute these things. You might do 15 minus 8 and then multiply that by 6. And here you might do negative 5 plus 11 and multiply it by 7. By the way, notice that you can apply the distributive property here and here. Just for practice, maybe you'd want to do that. Okay, but you don't have to do this, right? Because you say, okay, I know 1 is an equality. It's an equation. So what that tells me is that 7 is exactly the same thing as whatever I have here to the left of the equal sign. So this 7 I can replace with this expression here, 15 minus 8. Then I have a multiplication. And now the same here. You say, okay, 2 is an equality, which tells me that whatever's on the right side of the equality sign is the same as whatever's on the left side. So let me replace this whole expression by that left side expression, which is just 6. And now you look at the left side of this expression here and the right side, and you see that they're exactly the same. So yes, the equality holds. They're exactly the same things. Okay. All right, let's see. I believe we have one more. One more Yeah, we have one more. Okay. So this one says the following. Again, we have scales. So this one has a mass of 3. I'm going to stop drawing. Mass is actually, no, not 3. And then we have one more 2. On the right side, we have 5. And I have another set of scales, and this one has 5. It has 2 kilogram weight, it has 1, and it has 2, like this. Okay, now, suppose we place the weights from the left pan of the first scale on the left side of a new scale. Okay, and place the weights from the right pan of the second scale on the right side of a new scale. Will the new scale be balanced? If so, what equation does the new scale represent? So let's reread that. So we want to take the weights from the left hand of the first scale, so these guys here, okay, and place them on the left side of a new scale. And place the weights from the right hand of the second scale, so these guys, on the right side of a new scale. So let's do that. Suppose we have a new scale. So here below we'll have our new scale. So this first part, this first group of weights goes on the left pan of this new scale. So I put 3 and I put 2 here. 3, 2. This second group of weights from the second scale goes on the right side of this new scale. So I have 2, 1, 2. And the question is, will the scale be balanced? Well, again, look. These two, we'll call them 1 and 2 again. 1 and 2 is an equality. They're both equalities. Why? Because the total masses on the left side are exactly the same as on the right side, right? 3 plus 2 is 5, which is what I have on the right side. And of course, 2 plus 1 plus 2. 2 plus 2 is 4. 4 plus 1 is 5. And I have 5 on the left as well. So that's an equality also. So I see this group of weights, 3 and 2, and I look at my scale here, I look at my quality, and I say this expression, this whole expression, 3 plus 2, that's on the left side of this equal sign, is exactly the same as the expression on the right side of that equal sign, and that's a 5. So this whole thing can just be rewritten as 5. And I look at this expression here on the right side of my new scale. And I look at equality 2 and I say, oh, that whole expression is to the right of this equal sign. So it is the same as whatever is to the left of that equal sign. And what do I have there? I have a 5. So this whole expression can just be replaced with a 5. And now I notice that really what I have on the both pans of this new way of this new scale is 5s. So if I have 5 on the left and 5 on the right, yes, the scale will be balanced. So these exercises are just there to drive the point home that equality sign means whatever you have to the left of it has the same value as whatever you have to the right of it. So you can use the left and the right parts interchangeably. And if you add or multiply or subtract whatever it is you do to both sides of the equation, you are not modifying the equation still holds. Okay, if I have 5 kilograms to the left and 5 kilograms to the right, and I add, let's say, a kilogram to both sides, I still have an equation that is true. Okay, because I'll have the same value on the left and the same value on the right. Okay, so that actually ends the section on distributive property, and the next section is going to be on exponents. So we'll do that next time. So I will post a set of questions, set of problems on the Discord channel. You guys are welcome to try them out. They're good practice. And if you have any questions, I strongly recommend you try them yourself. I will post the solutions as well, but really try to do it yourselves before you go to the solutions. Okay, guys, I'll see you next time. Have a good evening.